This is the midterm demo for CAPER by Group 12. The objective of our project is to create a realistic and AI-capable animatronic of a parrot to be used in theme parks, for attractions and a variety of other applications. The important features of our project are that it will have realistic movement with a fast response time and fluidity. It will be able to detect when it is being spoken to and formulate a fast and accurate response to the user. Here are the engineering specifications. The ones of most interest to us and that we will be demonstrating are the success and speed of a response when the user pushes the input buttons, showing that the bird responds to its name, and demonstrating an accurate and fast response.
Here is an overview of all the main electrical systems for the CAPER's input-output control board. Starting here with the MCU, this is the Texas Instruments MSP430. This does all the low-level computing, taking all the various types of inputs, including the pulse streams from these 4 color-coded spring-loaded push buttons, and the selector switch, which has not been soldered on yet, so we're just using this jumper wire for now, which works just fine. Now that's the parallel communication to the board. All the serial communication is done through the MIDI opto isolator you see here, as well as the MIDI input jack, which is right there on the side of the board. Here is the dev board that will be used for all of the debugging, as well as some of the power, which is also provided by this triple channel power supply for now. One of the peripheral circuits used by this power supply is the Vox circuit. This is the voice activation circuit, taking the signal from this fine dynamic microphone, which will operate the mouth later. Here is the power supply that operates all the solenoids as well as the peripherals, and this 12-volt power brick will then supply the negative voltage to the Vox circuit. Here on the main body, you see the solenoid for the mouth, the head tilt, the tail flap, as well as the body tilt. The wings will be fixed to the body later on and will be powered by the tail solenoid.
Our chassis layout is as such. We went with a more basic approach when 3D printing this model, so we can manipulate it and format it as we please to fit our project and components.
Here we are demonstrating the fully manual operation by using the 4 spring-loaded push buttons. Each of those 4 buttons corresponds to one of the 4 movements: the mouth, head, body, and tail. To activate partial manual operation, you just have to flip the selector switch. This activates a function inside the MSP's code to automatically trigger the head, body, and tail. With this, you can operate CAPER completely hands-free, and this is where the Vox circuit comes into play. Using the Vox circuit, you're able to trigger the mouth actuator completely hands-free. As you can see in this video, the mouth is moving without any of the buttons being pressed. Now, depending on the microphone you use, the sensitivity may vary, but any run-of-the-mill dynamic microphone will work just fine.
Hello, my name is CAPER. I am an animatronic parrot. Hello. La, 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 la.
Once the selector switch is turned on, you'll be able to automate the head, body, and tail movements, leaving only the mouth movement to be completely manual, which can be controlled using either the push button for the mouth or the microphone and the Vox circuit, as you could see in this video. So, all 3 non-mouth movements, the head, body, and tail, are completely automated by the low-level MCU, but the mouth remains completely manual.
Hello there. Test 1, 2. Hi, my name is CAPER. I am working now. Finally, I will take over the world.
Or something like that. Now we are testing the specification on the push button speed. We're going through each of the 4 actuators using long and short button presses to determine the amount of time it takes to return to its resting state. Now, for the sake of time, we're only showing 3 of these trials, which means we're going to see each of the 4 actuators be pressed 3 times for 3 short presses and 3 long presses. The mouth looked really good, the head looks good. Now we're on the body. Body has the most oscillations out of any of the 4 movements, but still, it only takes about a half a second to return to its resting state, which is well under our 2-second prediction. Everything is looking great. Same with the tail. Lifts up nicely, lowers right back down with no oscillations. Everything's working great. Full success rate.
For the hardware test run, our initial goal was to create a response in under 2 seconds. We anticipated latency issues and lagging, among many other mechanical delays, but it worked out almost flawlessly. We can account for a 50 millisecond delay in the relays and a 31 millisecond delay in our code, among a few other mechanical delays as well, but our average response time for each body part is documented on the right. The mouth, head, and tail operated seamlessly and consistently, with the only real variation coming in for the body movement, slowing down to 270 milliseconds when it tilts forward. This still brings us nowhere near our limit of 2 seconds, so this testing was a success.
So here's one of the mechanical issues we ran into regarding the body actuator. If we were to press the body button and hold it down and then release it, sometimes it goes back up, but sometimes when you press it and then release the button, the body doesn't mechanically retract. Now, if you press the body button, you can see the relay is clicking, the solenoid is actuating, but it is not moving. Whereas then when you press, say, the head actuator, the body then retracts to its resting state. And now it works perfect. It works better with short pulses.
Our stack consists of OpenSSH for communication, Whisper.cpp and Llama.cpp as our libraries for ASR and LLM respectively, Mistral 7b for our Llama, our weights and biases, Python 3.10 for languages and C++ as well, eSpeak and Speedy Speech for our text-to-speech libraries. Alright, so this is my system. I'll get it started. And it is with the cable connected via USB. Alright, so this is the first run of CAPER's voice recognition system. As you can see, it is connected to the Jetson Nano right here, which is powering this monitor via an HDMI cable, and that is how you're going to get the audio. The DisplayPort cable is coming from this computer right here. So, as you can see, we have two separate computers, and when we run everything, these programs can run one at a time, or without each other's real interference. Let's go with that. We initialize the large language model. It is loaded within the computer's memory, as seen by NVIDIA SMI. And once that is done, we can actually start the application. This is the first run. System. What is your name, function, and tech stack? Who were you built by?
My name is CAPER. My function is to assist humans with their daily tasks. My tech stack is C++. My creators are UCF engineering students in Capstone project.
So this demonstrates a full run. The second run will be started. This is the second run. Here we go. This will be a bit of a longer conversation to demonstrate that CAPER's context window functions properly. System. Oh. System. How are you today?
Feel great. I hope you do too.
System. System. Who were you built by and for what purpose?
I was built by UCF engineering students for their Capstone project in 2024. My purpose is to help people learn more about AI, especially large language models, LLMs.
System. System. Are you playful or are you a serious parrot?
Oh, I'm not sure how to answer that question. I think it depends on who I'm talking to. If someone wants me to be funny, then I'll try my best to make them laugh. But if they want me to be serious, then I'll try my hardest to give them the information they need. So I guess you could say I'm both playful and serious at different times.
Here is run number 3. We initialize the Llama model, get the app to start running. System. All right, so I know about your functionality, but is there anything that you can't do?
Yes, I can't write code yet, but maybe one day.
System. System. Is that because you're a bird and don't have the necessary hands?
No, it's just that my creators haven't taught me how to program yet.
The accuracy for the responses was nearly 100% except for the stress test, which was 93.75, and our responses were at about 2 to 5 seconds for all of them. For the responses to name, we have an average rate of 71.7, so a bit lower than normal, but that was not one of our requirements. As far as test breakdown is concerned, we have successfully demonstrated that all of the criteria that we were aiming to achieve have been achieved. There are a couple of weaknesses still, but those can be fixed.
As far as the applications go for this project to be implemented, we thought of a few cases. CAPER would thrive in a theme park similar to the new ones opening in Orlando, for example, Super Nintendo World. An interactive exhibit with a talking character would no doubt add to the realness of the environment while introducing a great new exciting technology. As well, CAPER would do well in a show/performance role, acting as a real-time character for Q&As similar to Disney's Turtle Talk. CAPER's beauty comes not just from her performance, but also its ability to be malleable to the situation. The construction would be the same no matter the frame of this animatronic, so it can be shaped to any situation. Moving forward, our project is coming to an end. The remaining parts include full PCB integration, the physical construction of all parts of the bird, including feathering the outside, 3D printing a second model of the chassis, and interweaving every remaining part. Most of our functions work fine on their own, but we still need to combine them. We anticipate to be finished in a very soon timeframe.